For part 2 in chapter 19, we're going to talk about the coordination compound part of the chapter. Okay, some properties of these things and focusing on nomenclature. Because when we're dealing with a transition metal in the middle, as we kind of alluded to in the first video, we get some different properties, right? Because main group elements, right, 1, 2, and 13 through 18, right, those like to obey the octet rule. Right? We calculate formal charge when we have some exceptions, but there's a pretty clear set of rules for our main group elements. When we did Lewis structures, we talked about those in chapter 7 and 8. But transition metals are a lot different. Transition metals like to form coordinate covalent bonds, which we mentioned in the earlier video and defined in chapter 15 as well. Right? A coordinate covalent bond is formed from an interaction between a Lewis acid and a Lewis base, where the Lewis base is providing both of the electrons to form the new bond between the Lewis acid and the Lewis base. That gives us some different properties, right? We have mentioned the orbitals being closer in energy in the previous video. That imparts some color on these compounds, for example, which is different from what we might expect in the more defined organic world. So we'll get to why those things have different colors, but we need some more definitions before we get there. Okay? Our transition metal in a coordination compound or a coordination complex is a Lewis metal. Sorry, it's a Lewis acid. Transition metal is in the middle. It's a Lewis acid, all kind of tying together with one another. It is surrounded on the outside, the terminal atom, by ligands. These are the Lewis bases. And Lewis bases can be a variety of things. They could be an atom, it could be an entire molecule, could have been an ion. It just has to have at least one lone pair of electrons that it can donate to the metal, right? Because by definition, with a Lewis base, it has to have at least one lone pair. Okay? When we take the center metal and the ligands together, those add up to make a coordination compound. So the definitions you should know from here. You should know Lewis acids and bases from the past, know the center metal, which is where you find the transition metal, know the ligand, how it's serving as a Lewis base, and know coordination compound. That's what they form together. But we're also going to be paying attention to, in the event that our ligand is a molecule or a polyatomic ion, there's only one atom in there that actually has the lone pair of electrons on it. And that thing is called the donor atom. So you should know that definition as well. That'll make sense if we look at, well, not this slide, it'll look better in the 2 slides from here. Okay. Here we see scandium as the center metal, H2O ligands. Together they form a coordination compound. More definitions. The coordination sphere. Okay. Everything together, right? Ignoring the counter ion. Okay, so our center metal plus the ligands represented by a structure inside brackets because they're typically charged. Right? So jumping back a slide, everything inside the brackets represents a coordination sphere. The difference between this and a coordination complex is a coordination complex typically will include a counter ion as well. That's not shown here, something to balance the charge. We can also talk about a coordination number. A coordination number refers to the transition metal in the middle, and it's how many donor atoms are bonded directly to it, which is, well, not always, but can be different from the number of ligands, okay? Because we have ligands that can have multiple donor atoms. We'll see that in just a couple slides, which is what the last definition refers to. A monodentate ligand is a ligand that connects to the metal in the middle just through one atom. So what does that look like? Okay, here's a really nice slide to illustrate these principles. Okay, over here we've got monodentate ligands. Both ammonia and chlorine are monodentate ligands. Okay, because even though here the ligand is NH3, which is a whole molecule, and here the ligand is chlorine, which is just an atom, they're both just connecting through one atom, right? The only atom that exists over here, chlorine. And even though there's other stuff involved, those hydrogens aren't doing anything. It's just nitrogen that's bonding. So both of those are monodentate ligands, and in this case, nitrogen, because it's what is directly bonding, is the donor atom. What we have to be on the lookout for are polydentate ligands. This is where the ligand count and the coordination sphere can vary from one another. The coordination number can be different from the total number of ligands. Because a bidentate ligand is where I've got one ligand, but it connects to the center metal twice through two different donor atoms. And that's a subset of polydentate ligands. There are things that can connect 3 or 4 times. Right? Any ligand that bonds to the center metal by more than one donor atom, so 2, 3, 4, 5, 6, those are known as polydentate ligands. Okay, so bidentates are a subset of polydentate ligands. And polydentates are also known as chelates or chelating ligands. So here, this shows ethylene diamine, which is a common ligand. It's represented by the symbol En down here. Ethylene diamine is one ligand, but it coordinates twice through each of those nitrogens. So it's one ligand with 2 donor atoms. You see here how it bends and it's around on itself, and both of the nitrogens connect to the center metal, cobalt in this case. So over here, cobalt has 3 ligands because it's got 3 ethylene diamine molecules connected to it. But the coordination number of cobalt is 6 because it has 6 atoms that are directly bonded to it. We see that again over here with hemoglobin, okay, which is a polydentate. Here I've got one giant ligand, right, one big polydentate ligand, a chelate, and the coordination number of iron, even though it's one ligand, right, the coordination number is 4 because there are 4 atoms connected to it. Okay? And there's lots of examples of this. Here's another one, right? Platinum with 2 bidentate ligands, coordination of 4. So let's get into how to name these things, because coordination compounds have a rule for nomenclature, just like everything else that we would have learned in Chem 1. Okay. So if our coordination compound is ionic, we name the cation and then the anion, which is no different from any other ionic compound. So if it's just a cation and anion, put them together. That's normal nomenclature. We could have done that in Chem 1. Okay. But if we're dealing with covalent bonds, so things with high oxidation states, for example, we name these by naming the ligands first, followed by the center metal. And we'll typically have multiple ligands. So how do we separate those out? We put them in alphabetical order. If they're neutral, we typically just name the molecule, with some exceptions, right? Aqua, for example, is what we call a water ligand. If it's a negative ligand, so something that was anionic before it became a ligand, right, we add O to the root name of that anion. So that's the trickiest part, naming all the ligands, right? And if we have multiple of the same type of ligand, just like when we learned naming covalent substances, we put a prefix at the beginning, right? So if there's 2 ligands, it's di, 3 ligands, tri, 4, tetra, etc. The only tricky thing to look at, we've got a slide to cover this later on, is if the name of the ligand already has di, tri, tetra, penta, hexa in the name itself, we have to use a different prefix. So for example, ethylene diamine has the word di already in it, so I can't call it diethylene diamine. Instead, I call it bis. Bis represents 2, tris 3, tetrakis 4. But I use those only in the event that my ligand already has di, tri, tetra already inside the name. So I name the ligands, name the metal, and then I have to think about the complex overall, specifically paying attention to a counter ion. If my complex is positively charged, so cationic, or neutral, then I finish the name, and after I've named the center metal, I have to indicate what the oxidation number the oxidation state of the transition metal is. And I do that with a Roman numeral, just like when we learned how to name ionic transition metal compounds in Chem 1. If it's ionic or anionic, then I add ATE to the end of the name, okay, followed again by the oxidation state. So cationic or neutral, just leave it as it is. Anionic, it gets ATE. There are a couple of situations, nothing you would be quizzed on, where we use the Latin name instead of the name we get from the periodic table, right? So any of those situations on the periodic table where the symbol is something you wouldn't typically predict, right? Iron, for example, is Fe because it comes from ferrum, the Latin name. So when iron's negatively charged, we use ferrate instead of ironate, right? You won't be quizzed on those. One or two of them might pop up on your sapling. The challenge in the names, because we have to report the oxidation state, is using the ligands and the overall charge to actually figure out what the oxidation state is. So it's a basic type of math. You could effectively count it on your fingers. But you have to know if the ligands that you're starting off with were negatively charged or neutral. You've seen enough neutral molecules by now to be able to predict that ammonia, NH3, for example, is neutral, or water is neutral. And this table 19.1 here shows some common anionic ligands that you might experience. Okay, so any of those, any halide, right? Cyanide, nitrate, hydroxide, any of those are negatively charged, and that's how we name them as ligands. Okay, so fluoro, chloro, bromo, iodo, cyano, nitrato, fine, hydroxo. The only tricky ones are down here: oxo, oxalato, carbonato. And then we finish with some examples. 2 slides here showing examples of nomenclature. And you should work through each of these. Jump back and forth between the slides for the rules and these examples to work through how to name all of them. Okay. So let's just take the top one here, for example. Okay. How do I name it? Okay, well, I look at my ligand. It's ammonia, NH3. Ammonia as a ligand is called an amine ligand. So that's the first thing I start out with, amine. There are 6 of them. So it's hexamine, and then I name my center metal, cobalt. So hexamine, cobalt. How do I determine the 3? Well, ammonia, the amine ligand, does not have a charge. Okay, so that doesn't affect anything. What I'm looking at is the fact that my overall complex, which is represented in brackets here, is countered by 3 chlorines. Okay. Chloride is just a counter ion in this situation. I know I've got enough chem knowledge from last semester and what we've done so far this semester that chloride always has a -1 charge. And if there are 3 of them at -1 apiece, that's -3 total. So therefore, because these aren't charged, it must be countered by a +3 that's coming from cobalt. So I know the oxidation state of cobalt is +3. So hexamine cobalt 3, and then I just name the counter ion, chloride. Same thing down here, okay? Now I don't have a counter ion to worry about, but I've got a more difficult complex to name because I have 2 ligands. And notice the difference between chlorine. Here it's outside the brackets, so it's a counter ion. Here it's inside the brackets, so that tells me that it's a ligand. Okay? So I name my ligands, amine ligand, chloro ligand, and they go in alphabetical order. So I name the amine first, 4 of them, tetraamine, and then 2 chlorines, dichloro. So tetraamine, dichloro. And notice, right, you're just paying attention to A from amine and C from chloro for alphabetical order. Those prefixes, tetra and di, do not change your alphabetical order. So tetraamine, dichloro, PT is platinum. And then how do I know that it's platinum 4? This is the tricky part, right? Because the overall complex has a charge of +2, but I didn't put 2 in Roman numerals there. Amine is a neutral ligand, but we just saw the chloro ligand is negatively charged. So both of those had a -1, and it gave me +2 overall. So a -1 and a -1 to give me +2 overall. It must have been platinum 4 +4 to start. And there's no counter ion, so I just name it tetramine dichloroplatinum 4 ion. 3 more for practice over here. This is the ethylene diamine ligand down here. So notice when I name 3 of them, it's tris, not tri, because it's got di already in there. Okay. Water ligand is aqua, so you see tetra aqua. And then another slide with more practice where the complex is neutral, and then as an anion, so that's when we get the ATE ending. Make sure you try all those for practice. You'll have additional on your sapling as well, and post on Blackboard to discuss if you have any questions.